Hello. Thank you for attending to this session. So in this session, we are going to talk about quantum communication, more precisely quantum cryptography. I would like to say congratulations to David for doing such a good job explaining too many complex things related with quantum physics. So I am Aitor Brazaola. I come from the TECNALIA Research and Technology Research Center, and let me present briefly myself. So I have a background of computer engineering, and currently I'm doing a PhD in quantum communication and QKD networks. I have had the opportunity to work in diverse projects from IT security in industrial sector and in service management, and currently I'm doing my job in TECNALIA. Well, but before starting to talk about what is the point of this talk, we have to understand what is the point of these technologies, like quantum cryptography or post-quantum cryptography. First, we have to understand what many more people have been anticipating during the past years, and the projections suggest that million-qubit systems are close to be a reality in our days. And our current cryptography relies on mathematical problems that these computers can potentially solve with certain quantum algorithms. These algorithms, as has already mentioned my previous colleague in the previous talk, there are mainly two or three. But the most famous one are these two. The source algorithm, which is an algorithm which makes quantum computers to easily factor large prime numbers. And these directly attack to the public key cryptography that we have today. Like, for example, the cryptographic schemas like RSA or ECC that we are using for signing our identity and also for guaranteeing the integrity of information. But on the other hand, we have also another quantum algorithm that directly attacks the other kind of cryptography that we are using today, the symmetric cryptographic schemas, like we are using, like, for example, AIS, 256, and so on. This kind of cryptography relies on a different mathematical problems, but it is also affected by this algorithm, which allow potentially to quantum computers to brute force the search of symmetric keys in a certain range of sizes of these keys. One of the solutions to this could be to increase the size of the keys that we are using in AIS, but at the same time we have to start finding different approaches to classical cryptography. The predictions, as I already mentioned, are that in the near 10 to 15 years, we will have these competing quantum computers. So we have to start preparing now. OK, but what are the options that we have now on top of the table? Well, we primarily have two options. And I'm just going to mention briefly the first one, because many other talks will go more deeper into them. In the first hand, we have PQC, or post-quantum algorithms. Post-quantum algorithms are classical algorithms that rely on mathematical problems that are not affected by the known quantum algorithms today that I presented in my previous slide. And this is very important to say today. The other hand that we have is QKD, or quantum key distribution. Quantum key distribution, in contrast to a post-quantum algorithm that uses classical mathematical algorithms, it uses quantum mechanics for ensuring the security of the information that is being exchanged between two different parties. So in many talks, they are discussing about which one is the best path. I don't think that there is a best path between these two. Both are complementary. And as we are going to see later, for implementing one, you will need probably many more resources than the other. So maybe you will be interested to implement a certain solution for certain problems and another different based on post-quantum cryptography, for example, for many others. But just briefly presenting what we have in the first path. In the first path at this point, we have the three finalist algorithms of the process of standardization carried out by the National Institute of Standards and Technology from the United States. These three algorithms are one, a key encapsulation mechanism, and the other ones are digital signature algorithms. The first one will allow us to exchange shared secret between two parties over an insecure channel. And the two others will enable us to signature and authenticate information in a secure way. All of them, all these three, are based on the same family of mathematical problems called lattice, but with slight difference between them. And quantum key distribution, which is the other option that we are going to cover on this talk. In quantum key distribution, we have to think of it as a cryptographic primitive. What is this, a cryptographic primitive? Well, this is not just the whole solution to a cryptographic usage in our classical communication, but it solves one of the key points of our cryptographic processes carried out in this communication, which is the key exchange problem. Without such secure key exchange in our communication, all the rest of the cryptographic systems that you will implement are lost, because the main seed for strengthening this security is going to be broken. QKD, as I said, protects using quantum mechanics of photons. In this case, we are using this implementation of the qubits, but as we are going to see later, there are many more. And unlike other capacities, unlike other solutions, this is the only one that is independent of the computational power of the attacker. So there is no point of the power that the attacker in terms of computational capacity and so on, because this is not related with maths. The first protocol was designed by Charles Bennett in 1984. So the underlying technology, the underlying theoretical concept, are not new. What are new are the implementation and the companies that are starting to develop their systems and starting to sell in the industry. This can be available in the market, but usually the prices are high at this point, but the provision they are going to lower in the next years. But first, let me introduce briefly what the qubit is, because it is important to understand how it works and how we can encode information in it to understand all the rest of explanations that I'm going to cover later. The qubit, as the classical bit, is the minimum unit of information that we are manipulating in the quantum world. It's an abstract concept. It is not associated with a specific physical system. As I said, we can use photons, but we can use ion trapped and many other technologies. And it has two states, distinguishable by physical measurements. The main characteristic of the qubit is that these states can be in a superposition continuously until we measure it. When we measure it, we provoke the collapse of this state. And depending on how we are performing that measure, this outcome will be one or the other. Will be the value that has been encoded initially, or maybe a 50% of probabilities of obtaining 0 or 1 value. This is very, very important because independently of the value that we have encoded in this qubit, it is not the same to first measure in one axis and later in the other, or in the opposite way, because once we collapsed in the wrong axis, the qubit could have a completely wrong measure since it has been encoded in the init. As I anticipated, there are many more implementations of qubit. In this talk, we are going to talk mainly about photon, but there are quantum dots, nuclear spin, superconductor, as they are anticipated before, and so on. But first, to introduce how QKD works, I would like to explain just briefly how it works, the most famous QKD protocol, and the first QKD protocol that it was invented, in fact. So these are Alice and Bob, who are trying to communicate with each other, with Eve in the middle, acting as an eavesdropper. Alice and Bob share two channels mainly. The first channel is a classical channel, which is a fiber optic channel, and the other one is the quantum channel, which is the channel which they are going to use to exchange the qubit between themselves. First, they have to perform the phase of prepare and send. In the prepare and send, Alice, which is the emitter, has to generate a random sequence of bits with a quantum random number generator, which uses the same technology, the same quantum technology that is going to be used for encoding the information and transmitter over the fiber. So once Alice has generated a sequence of random bits, Alice has to generate also a random number of access, which is going to be used for encoding this information into photon qubits. Then Alice sends that information encoded in qubits over the fiber to Bob, and they start the second process, which is the key shifting. In the key shifting, Bob, what he's going to do is to measure each of the qubits that are being transmitted by the quantum channel by Alice in a random ways. So Bob is going to have certain points in which is going to be success measuring the qubit that Alice has prepared in the right axis, but many others are going to be wrong. In the key reconciliation, what they do is to remove all those qubits that has been measured in the wrong axis, because one of the information that Alice and Bob are going to exchange over the classical channel is the axis that Bob has been used for measuring those qubits. Alice is going to respond to those list of qubits, saying these axes that you have used for measuring the qubits in this position and this other are wrong, so you can discard them. The remaining qubits that they are going to share are classical bits, which has been collapsed by the qubits using the same access, and at the end, they should share initially the first shared keys between them. But this is not the end. But what happened, how they check if there is someone in the middle collapsing in a wrong axis these qubits? Well, what they do is the key reconciliation, and in the key reconciliation, Alice sacrifices some certain qubits that previously has been exchanged and verified by Bob using the same axis, and discard them. But then they check in the public channel if these classical bits are the same. If they are the same, everything is correct, and the key can continue to the next phase. But if some of these supposedly agreed bits using the same axis over the same qubits, some of them are wrong, these are indicating that someone in the middle is collapsing this information in wrong order. And probably if the level of errors that they identify in this phase is higher than a certain threshold, they cancel the communication and everything is restarted. At the end, they just launch a classical process of privacy amplification, where what they do is to launch several hashing algorithms to try to remove as possible the possible leaks that someone in the middle could have get of this information exchange, even with all these previous checks. Well, we can categorize these QKD systems, these QKD apparatuses, depending on the technology that they use. In the first hand, we have the prepare and measure systems, which are the systems that are more similar to the BB84 protocol that I previously explained, where Alice prepares first the sequence of bits and sends them over the channel. And the other one is the entanglement base, which uses the entanglement properties of quantum physics to create pairs of photons, which are going to be shared between the two pairs of the communication, in this case between Alice and Bob. And sometimes this kind of system usually have an independent system, which is going to be the photon source, which is going to prepare the source of information in photons and be distributed over the two parts of the communication. It is important that the classical channel, yes, it is classical because the information that is going to be shared in that fiber is classical signals. But it is very important that this channel, it is authenticated. For authenticating this channel, usually this kind of systems uses a pre-shared keys mechanism. where first, to start up the system in the first place, someone will have to extract a random generated key in one side of the communication and transport it manually to the second part of the communication. Just after that, this process of refreshing these pre-shared keys is going to be seen by the quantum keys that are going to be exchanged securely by the quantum channel. So this is important to take it also in account. The authentication phase of the classical channel also consumes part of the cryptographic material that both systems are being exchanged between them. Well, another kind of categorization of these systems could be the type of protocols. The light has the particularity that it can behave as a wave, but also as a particle. And depending on what are we considering of this, the photon, we can encode information in different degrees of freedom of these signals. In the first hand, if we are considering the photons as a particle, the particle has some properties, like, for example, the polarization, which is what I already mentioned in previous slides. We can build systems which encodes information in the polarization part of these particles. These kind of systems usually are best designed for long distances. These systems are also require more precise hardware, more precise modeling of the detectors and so on, because for codifying information in the properties of light as a particle, like the polarization, we will need very precise optical components. Very complicated. At this point, it's very complicated to generate single and independent photons instead of relying on a laser source, which is going to be firing bursts of laser pulses. On the other hand, we have the other ones, which are the continuous variable. The continuous variable means that we are using other properties of light when we consider the light as a wave, like, for example, the amplitude, the phase, and so on. These are more extended in the industry because it's easier to manufacture, because for creating these kind of systems, there are many electronics that are already being used for classical telecommunication systems that can be reused for developing these systems. And these systems will also are better integration with the telecommunication grade networks, because can be multiplexed with the rest of the information that are being exchanged over the networks. Well, but these systems, they could also have been vulnerable to side channel attacks. These systems, in the theoretical way, they are completely secure. As I already mentioned, they are information theoretically secure, which means that there is no way to break these protocols with computational power. But the problem is with the implementation. If we are, for example, encoding information in different degrees of the laser source of our equipment, we are allowing to a certain third party to start leaking information, spying information on of those degrees of the light, like, for example, different frequencies of the light, which we are not controlling in the receptor, but they are being also encoded with the same information of the controlled frequencies. So if someone in the middle will be inspecting these degrees of freedom, we never will be able to detect that these qubits are being collapsed in the wrong axis, for example. Many other ways, like, for example, intentional emission of light, in other ways that we are trying to encode in the original emitter, that can lead to, for example, making to check if the specific optics that we are using in a device have this kind of defect or the other, and infer if we are receiving the correct information or not. Well, I've been talking about fiber optics all of the time, but QKD, it is not limited to fiber optics. Actually, QKD, as I already mentioned, is photons, and photons can be transmitted over the atmosphere also, and over the water include. In this case, the most relevant use cases are with the space links. Space links are very useful because overcome the technical distance limits of terrestrial fiber optic networks. Normally, these systems has a limitation of 100 kilometers, 200 kilometers using the same fiber optics because the degradation of the quantum channels over the quantum over the fiber optics are so high to keep the consistency of the information. So QKD Space Link could be a solution for enabling QKD networks which are covering a wide range of kilometers or intercontinental links. But it has also many challenges, like the ones that you are seeing here, like it requires a precise tracking and synchronization, and it could be obvious, but you will need a satellite. It is not common to have your own satellite. But there are many examples that are, well, not too many, but there is a relevant example that demonstrates that quantum key distribution can be extended using space links. And this is the example of China. China has 700 optical fibers and 2 satellite links covering a wide range of 2,000 kilometers length of terrestrial coverage. And they were the first to launch a satellite called Mithrius that enables BB84 protocol with decoy states in the space. They are using this network for serious things, not just for research purposes. Yes, they do research, but they are doing service for more than 150 industrial users from many sectors different. And what are we doing here at the European Union? Here in the European Union, the European Commission is also pushing forwards the program of EuroQCI, which is the European Quantum Communication Infrastructure. At this point, EuroQCI is pushing hard to the efforts of each country to develop their own national quantum communication strategy and to building quantum communication networks between them, and also to establish a standard to share these communications between different countries that belong to the Union. They are also preparing the first launch of the satellite, which is going to be part of the IRIS-2, which is the secure communication system in the space from the European Union. And it has the same application areas as we have seen before with the China QKD network. The experts in this field are also proposing that one of the main challenges for doing this is to establish standards to communicate different quantum networks between different states, because there are many different manufacturers, many implementation of trusted nodes which are going to be the relay between different quantum links and so on, and there is a strong need of standardization in this part. Here at TECNALIA, we have our own laboratory of QKD, what we are using for integrating this technology in the existing project with our customers, doing research also of quantum key distribution networks, how to enhance the privacy of this network, which involves many classical components in them. Well, we put these devices into the hands of our customers for letting them experiment also with quantum cryptography. But there are many other hybridizations of other technologies which are going to enhance and improve the distance coverage of quantum key distribution networks, like, for example, the SDN, the software-defined networks. Software-defined networks are going to enable to perform better routing between relay nodes in a quantum key distribution network and intercept or avoid those quantum channels that has been received a denial of service attack. For example, intelligently deviating the information on the exchange of 2 keys between 2 distantiated parties over different quantum links, which are performing correctly. One of the other remarkable advancements that are currently receiving this technology and what many partners of the industry are working on are in the photonic chips. At this point, quantum key distribution devices are very heavy load and very big devices that make a lot of noise because of the ventilation that they need to perform the exchange of this information securely with these 2 channels, as I already mentioned, or more physical cables. But they are working on photonic chips. Photonic chips chips will try to miniaturize all this technological package into a chip to be integrated easily in our computers, for example, or in network electronics, like could be a router or an encoder or so on. What are the application fields? Well, I think that all of the people that are here are probably imagination what are the applications that such a technology like this could have in our communication. But as I already said in the beginning, when I was comparing post-quantum cryptography with quantum cryptography, I think that quantum cryptography at this point, it will try to cover those communication links that it requires a very high, or let me say critical level of privacy, like could be diplomatic cables, for example, or defense networks, or some kind of critical infrastructures that are, because of their name, critical, and it cannot rely on the uncertainty of having better quantum algorithms that will cause the post-quantum cryptographies to collapse. Encryption, authentication of endpoint devices, network infrastructure, the backbone of the networks could be enhanced with this technology, and, well, industrial appliances like, for example, protocols related with SCADA, energy sector, and so on. One of the key experiments that we carried on here at TECNALIA was to bring these devices to two power plants separated between 50 kilometers one of the other, and to test how they work using their own fiber optics, and it was a huge success. We have also to use cellular networks to interconnect the classical channel, and performing this classical, this hybrid mount, it was a high success. Just to briefly mention, the European Telecommunication Standards Institute is developing a lot of standards related with this technology, which is going to push forward the adoption in the industry and in the sector like governmental and so on. I recommend to check them because they are trying to cover all the engineering most concerning parts of this technology. Just to finish, I would like to thank you to my audience to be here, and I hope you enjoy this presentation. Thank you very much.